Hello everyone, welcome to another video on shell coding on ARM Linux 32-bit course presented on YouTube. So in this video we are going to introduce ourselves with the ARM architecture and registers. Giving you a small overview how a computer works is there exists a CPU that loads data from memory. It can be any instruction, it can be an executable or a video, processes it. Depending on the situation, writes back that processed data into the memory or either represent it to the output device like monitor or printer. So this was the only thing you may need to know. Let me introduce the basic structure of an ARM binary. So a basic ARM program can look like this in a debugger. So there exists some kind of instructions like this push instruction, load instruction, branch instructions. It might seem gibberish to many of you because you haven't encountered any kind of assembly programs yet, but upon completing the module 1 successfully, you definitely may be able to understand what are all these instructions doing, what is the outcome, what is the result of all these instructions. So stick with the module 1 and you will know everything what these instructions are actually doing. So moving on to the further slide. So the building blocks which a binary, whether it is of ARM or Intel, a binary which requires to run on a computer requires three major things: registers, stacks and instructions in it. So any binary which consists of these three things is a proper binary, can be executed on a processor and perform some operations. So we are going to talk about registers here. Before talking about registers, let me give you an internal overview how a CPU looks like. So there exist some blocks, like I have represented 8 blocks which represents 8 registers in it, although ARM 32-bit processor have 16, but for demonstration purposes I have represented only 8. So these are all small memory banks that is used to store data inside the CPU, and the data which is stored in these blocks is computed by this ALU or arithmetic logic unit. Upon just computing the data stored in these registers and storing the result back to these registers, the process can just take these data stored in these registers with the help of control unit. So you can think that control unit is the gateway by which data stored inside the CPU or in the registers can be passed through and fro by any process in a computer. So without control unit, your CPU will be just self-computing, self-storing piece of you can say metal, nothing else. Because of the control unit, the processed data is moved wherever it wants. Talking about the registers in ARM 32-bit processor, there are 16 general purpose registers, or general purpose we can say the processors we can use to create our own program. Those varies from R0 to R15, where from R0 to R6 these registers are used to store the arguments passed to a syscall. So the syscall is stored in R7. If you think what a syscall is, so syscall is a number, a specific number by which the computer analyzes what the program wanted to do. So for reading it have 3, for writing it have a syscall number 4. So the computer can just identify what the process is actually asking for. Talking about the next register set, R8, R9 and R10, these are all used for fast interrupt query. This is not helpful in terms of shell coding, but if you wanted to know about FIQ, you can just refer to the ARM documentation. R11 is the base pointer or the base address from where a stack frame or a function starts. R12 is a scratch register. This is also not helpful for shell coding. You can just refer to ARM manual if you want to learn about it. R13 is a stack pointer which points to the top of the stack. R14 stores the return address of a function, means when a function returns, the data in this register, R14 register, will be used to execute next. R15 stores the program counter. So what a program counter is? A program counter is a register which stores the address of the next instruction to be executed. So if you are pointing to an instruction like move EAX and move R1 and R1, then the program counter will store the instruction after that instruction. If you don't get now everything about R15 now, don't worry, the query will be resolved. Let me introduce the simple C program where I am just printing out the data passed into the arguments. So as we already know, the syscalls for write is 4, and we also know that syscalls are stored in R7 register. The first argument is stored in R0, second in R1 and third in R2, and those are the file descriptor pointer to the string which we wanted to print. The count of the numbers, the number which we wanted to write to the standard out file number. So after loading all these registers with their specific values, how can we just execute them? Is there anything we can just do? So there comes a concept of software interrupts. So software interrupt is like an invocation of the kernel by which your process invokes the kernel by an instruction called SVC, which is supervisor call. So it allows your process's data, registers data, to be executed by the kernel. Then kernel just looks up for the data, like R7 stores a write syscall. You can think of like doing a kamehameha of a process. Process just gains a superpower of their own just using the SVC instruction. Looking up for another register, it is CPSR or current program status register. So it is a register which we can use to make choices in our program, like the if else statement. Because of the values stored in these registers helps us to make choices. The concepts of CPSR, the values like NZCV, what are all these stuffs, should be cleared in next video, because without the concepts of instructions you may not be able to understand why these bits changed. So stick to the video. Also talking about more registers like the APSR or application profile status register and the system control register. These are for the developer's perspective usage. So if you want to know about, refer to the ARM documentation. Understanding about these things are of no use if we are learning about shell coding. Moving on to the end of the video. If you have any question related to this video, you can just ask in the comments section. Drop the likes and subscribe. Download the PDF in the description, which includes all the slides used in this video. From there you can just locate to my Twitter and GitHub handles too. You can follow me too. That's all for this video. We'll meet you in the next one.